So that brings us to the second movement, whimsy. It's a quote from Moby Dick. It may seem but an idle whim, but it has always seemed to me that the extraordinary vacillations of movement displayed by some whales indirectly proceeds from the helpless perplexity of volition. So it's nice. I mean, I think Melville is aware of the fact that this is a big cognitive beast that moves around in interesting ways. He's actually describing how it moves around when it has 20 harpoons stuck into it, which isn't what I studied. But there's sort of an awareness of sort of behavioral oscillations and movement. So what I have studied, what I actually have done, is I've gone to these places in eastern Russia and I've looked at the fur seals. And I've kind of slipped around on these rocks, like my colleagues over there, and captured these animals and put all sorts of stuff on them and let them go. And these things are, there's a GPS detector in here, there's a sensor which is related to stomach temperature sensor, which can like measure when it actually consumes food, and there's a diving piezometer type thing. So this is a well-instrumented animal. It's out there collecting data, which we then gather. And this is a bunch of tracks, foraging tracks. So that was a female fur seal. They aggregate in huge colonies. They give birth, they nurse their pups for a couple weeks, and they head off on these trips. These trips can be, several days long. And a lot of animals do stuff like this, like penguins, for example, just on the way, a lot of pinnipeds. Foraging. Foraging is really important because feeding the pup, there's a lot of the survival depends on the success of feeding the pups. So that's the data. What do I do with this data? Well, again, the whole complex thing, what it really did is it parsed everything into these persistence components and turning components. So this is what I recommend people do with track data. You parse it into persistence, which is just that speed, estimated speed times the cosine at theta, and a turning, which is that times the sine theta. This captures sort of a tendency to turn, and the variability of turning, and the autocorrelation possibility of turning. And this persistence tells you about how fast it's moving and how much behavior is changing. There's a lot of information if you look at these variables, as opposed to turning angles and velocities themselves. The biggest advantage probably of that is that velocity. So velocities, as we know, are kind of unimodal and right, sort of long-tailed, positive, not very normal, not easy to model, sort of in a sort of standard time series ways. But these two components are basically mixtures of normals. So they're basically Gaussian, and that distribution of this persistence and this turning is Gaussian. And the turning will typically have a mean of 0. Always have a mean of 0 because you should turn to the left about as often as you turn to the right if you're a symmetric creature. And that is probably like even more than all this stuff about what it means. The fact that you can model these really well with very standard time series techniques is extremely powerful. So we can model these as sort of local AR1 processes, autoregressive time series processes. This is an autoregressive time series, and if we look at what happens when you subsample it at different intervals, we see that the autocorrelation drops with time. So this time series can be characterized by 3 parameters: a mean, variance, and some fundamental autocorrelation, which in practice depends on the time interval. So at a certain time, every minute or something, you might have a very high autocorrelation. Every hour you might have a low autocorrelation. And the relationship between the hour autocorrelation and minute autocorrelation would be the minute correlation to the 60th power. And that's important because the intervals in the data range from a couple of minutes to a couple of hours. If we want to say anything about it, we have to be able to take into account that gappiness. But because it's Gaussian, we can write out the distribution of the data, and we can get a likelihood, and we can estimate that row. So we can estimate everything in a gappy time series. So here's an example. There's a true time series here. There's 1,000 points in here. The autocorrelation is 0.8. I took 100 points out of the whole thing, I ran it, and I got an estimate of 0.78. So the fact that these points are all over the place, the intervals are really regular, is totally trackable. And then you might have structural shifts, right? So this is what's really interesting. This is where, okay, so this particular time series, if something happened in there in the middle, this is where it actually happened. The mean changed, the variance changed, maybe the autocorrelation changed, we don't know. But we can get the likelihood, assuming all these different parameters, kind of sweep the whole thing, and we see, okay, well the likelihood peaks there, so the change happened somewhere around there. So that works. And it works very well. So here's data where that's just very, very sparsely sampled, but it still picks out the likelihood very well. And it's very, very few points in here. There's more points here, but the only difference here isn't the mean or the variance. It's that autocorrelation, and it does an excellent job of picking out changes in autocorrelation from gapping time series. So this is sort of the basic unit of our analysis method. It's great that we can find a shift. This tells us where the shift is. There's all sorts of different things that can be changing. Nothing can be changing, or everything can be changing, or any combination of parameters in between. So we can apply some sort of criteria, likelihood-based criteria to decide. And it turns out that this Bayesian information criteria does a very good job of, these are simulated breaks. These are like, the circle sort of reflects how often the BIC chooses a particular model. And so here it chooses most of the null models correctly, which is important. Most of these single parameter models correctly, which is important. And it just does a good job all around. So we can also take the, a real time series has a lot of changes going on in there, but we can get those too by selecting a window, finding the most likely breakpoint, identifying the model 6, where the means and variances are different, but can detect the difference in the autocorrelation, record the estimates, move the window forward, and just repeat. And so there it goes, crunching through the data. And this is, the output of this thing is sort of a synthesis. It tells you where the likely breakpoints are, and it gives you sort of an average estimate of what all the parameters are in each of these sort of intervals.